All right, so this week we have David Liu from Intel. David is a technical consultant engineer at Intel Corporation in Austin, Texas, where he represents Intel's Python products and projects. He's focused on solving customer problems in Python while simultaneously developing and shaping Intel's software products to match customer needs. So he's worked as a software engineer utilizing Python in machine learning, network infrastructure, and web work. He holds an MS in software engineering from UT Austin. So with that, yours, David.
All right, thank you. Thank you for the great introductions. David is my name, and for the type of role that I have at Intel, it's a very unique role. And one of the things that I do with a lot of the customers is I try to understand the needs that they have and try to look a little deeper and figure out where the actual performance problems are coming from. And in the world of Python, that can actually be pretty confusing. So for a lot of those that are really getting into kind of the engineering, math, science kernels, the problems that you need and the tool sets that you need to diagnose those problems become a lot more specialized. And so hence, in making this presentation, that was one of the kind of the guiding insights and one of the things that I'm hoping that you guys get out of this presentation. So without further ado, I'm going to go ahead and get started. And one of the things that I'm going to go over is the native performance libraries. Now, some of these, hopefully, you guys have actually gone through in previous presentations in this series. We're going to go a little bit over just how Python performance is actually handled and what things we're looking for when we talk about Python performance. And then also the types of scientific computations and engineering that are done. So, if you are in a math, science, or physics class, or if you're doing something in that space, what type of computations you're going to be looking at, and what types of further numerical tools that you're going to try to utilize to get the most out of that code. And then finally, we're going to talk a little bit about the advanced algorithms and applied transforms that are used in this space. And hopefully, that'll also lead into the next presentation that will follow mine. All right, so let's go ahead a little bit and talk about just Python usage in academics and industry. So one of the things that I think comes as a surprise to a lot of people is why Python usage is growing in the industry and academic space. And for the first one, it's the verbosity that we had in previous languages. I remember when I was in undergrad, it was just a lot harder to get things done. And that was kind of the days that Python was starting to get its roots. And then as further went along into my master's, I was able to see that the types of tools and techniques that it was providing students was extremely powerful. So as a teaching tool, it became extremely powerful. Now, that then translated into industry usage because of its roots in industry usage. And from that point on, I think the types of frameworks in the open source community helped grow it in that perspective. So in terms of meeting the needs of math, science, and engineering, it's one of the few languages that have specialized libraries that are built for it and a very dedicated following that continues to make contributions in that space. So that's why Python today is used so much in a lot of things, from numerical work to infrastructure work to machine learning work. You're going to see it in a lot of places, and the reasons are for those baseline performance libraries that have been included and have been continued to be contributed to over the last 10 years. So to just kind of give a brief explanation of Python, I know a lot of you have probably installed it. Some of you may be well seasoned, so this may be information you already know. Python is an interpreted language that's actually built on top of C, and so the base interpreter is CPython, and so it's a very high performance general purpose language that focuses on kind of the powerful libraries that come with it. So it's been seen as kind of the glue layer between a lot of languages, between a lot of workflows. And so as such, one of the things that people have tried to do is to understand, one, where the performance bottlenecks are occurring and how to negate those if they do exist in the language. And that's been something, at least in the last few years, where they've been trying to look at the base language, not just the numerical packages, and try to look for that. But in so doing, we're finding where some of the in-between areas can actually be optimized. And so we'll go into that in a little bit. And then also another key point here is that It's also a trending example of one of the things that we see a lot now today, which is the high-level programming languages, a lot of them interpreted. We're seeing a lot more of them actually starting to appear. And the reason is people need to get things done faster. And so when using Python, one of the key things that motivations behind a lot of people who use it and develop it is they want to be able to get something done quickly and get it done in the least amount of lines in the most maintainable way that they can. And let's just talk a little bit about Python performance. So how many of you in this room think that Python is high performance? Very few of you, and you're probably right? The creator of the language actually did not want it to be a high performance language. They wanted it to be a language that got things done. The focus wasn't to be fast. However, in so doing, I think from the usage of the language, people were finding that they wanted to use it for other things. They had a different vision of it, and that's kind of the joy of the open source community, is they'll start using things in very different ways that maybe you didn't intend, or you may have intended. And so Python then became kind of the de facto language that some of the people started their bigger projects on, because they liked maybe the syntax or the way that the language was parsed, or they liked some of the focuses of the language off the get-go. So again, the focus of the language was supposed to be expressive and quick to prototype. And with that, how do you actually have that type of language flexibility while still having performance? That's the big question for a lot of the customers that we talk to. They said, we have a lot of engineers coming in that are new graduates. They're used to Python, but then our code bases, we're starting to migrate our code bases, and now we're starting to find, well, how do we maintain that performance as we migrate our code base to something that's more maintainable, and also grow new code bases in that sense. So let's just go also to how Python works. So how many people have actually looked at the Python bytecode before? Okay, very few of you. So Python is very interesting in that it actually has 4 distinct steps when you actually use the Python interpreter, right? You have, from your Python code, it lexes, parses, compiles, and then interprets your code. So there's kind of 4 distinct steps, and there's optimizations in every single one, but the one that really has kind of the biggest benefits is after either the interpretation stage, or is either at the interpretation stage or after, and a significant amount of it is actually after. And so we'll go into that with the native performance libraries. This is mostly true for numerical scientific engineering work. And the compiling is not exactly what you think of when you think of compilation, right? It's not that standard. It doesn't go down to x86 instructions or anything similar. It instead goes to a code that's used for the Python interpreter. So the interpreter itself is doing some of that mini-ish compilation that's actually for it's used for language flexibility. So when you have kind of loose type checking types of semantics, that's a lot of what that final step, that interpretation stage, is actually doing for you. That's why it doesn't actually put everything directly into x86 instructions. So you may ask, why does this actually matter, right? Well, that's because Python usage, and especially in this space, has a lot of different layers, right? And you have that first interpreted stage that you're going to use it with, and then it has kind of various trade-offs. So how many people are familiar with the global interpreter lock? OK. So the global interpreter lock, or the GIL, right, is to ensure single-threadedness of the Python application itself. And in so doing, you don't have these issues. You don't have a lot of race conditions or kind of these seg-faultish type of things when you try to do concurrency. And it creates a safety, and a lot of people have been trying to get rid of it. So there's actually been a movement to try to remove the GIL. There's been a lot of things, but it's implied safety. And that's also one of the reasons that the language is actually very popular, is it does have this implied safety. But it can be a limitation if you don't know where it is, what it's doing, and why it's there, right? And so every one of those things has trade-offs. So if you're using the base language, you're usually going to be in that land where you're just using the base interpreter, and you're going to be okay with that global interpreter lock, which usually never really rears its head unless you do a lot of long asynchronous calls. Okay, they're usually kind of I/O-bound type of problems. With NumPy, that's one of the performance libraries, so hopefully some of you have already seen it, which is numerical Python. That's a very, very highly optimized numerical package that allows you to do numerical work while staying in the Python language, but it's actually calling all the way down to kind of custom-built layer of C, where they've done optimizations that are specific to numerical work. So in so doing, you can essentially get around the global interpreter lock. You're essentially exiting that layer of Python and immediately going into the C space. So it's actually very fast. That's why it's very, very close to native C, right? And that's why you can essentially bypasses that. You get multi-threaded, multi-core performance. You get a lot more access to kind of some of the hardware-esque type of optimizations that you normally wouldn't get at the base Python language. And typically, when you are in Python, if you're not using a specialized framework for something, you might be doing it wrong. Usually, somebody or some other type of project already exists where the type of optimized work has already been done, and you can use it from there. And the concept is just Python is the glue layer at that point, and you're only staying in it maybe 5 or 10% of the time. And again, for best performance, you want to be escaping that layer, and that's why if you look at, say, the profile of some of the code that runs in numerical Python, it actually only stays in Python for maybe 5, 10% of the time. The rest of the time, it's actually in C, and we'll look at that in a sec. And with, as I describe these layers too, one of the other things that you may notice is that there's a layer even underneath NumPy, and what that is kind of this call down to a optimized linear algebra framework, which does a lot of work. It's usually the BLOS layer, and occasionally it can actually be the bottleneck. And BLOS stands for Basic Linear Algebra Subprograms, I believe. So essentially, if your code is essentially using NumPy, but it's having to go back through the Python layer, so this happens more with really, really custom workflows that may be domain specific, then NumPy or Python could actually be your bottleneck. And at that point, it's actually best to write that complete part in a high performance native performance library, usually written in C. So like the Intel Math Kernel library would be a great example, which can also has parts of the BLOS API, but then has other extended instruction functions that are contained within it. And again, dispatching to hardware vectorization is important. Did they talk to you about hardware vectorization yet? Yeah. Okay. Cool. So we can get over that one. Okay. So let's take, for example, an example with array loops, right? So I think a lot of you are familiar with just a general for loop, right, in Python that you can do. And normally, what it does is essentially it's in its single threadedness, it'll operate on the first loop, the second loop, the third loop, et cetera, et cetera. And so the GIL will actually enforce that it stays in that, there's only one single Python binary process that can run that at any given time. And to really escape that, you need to be using an optimized library. So let's take, for example, NumPy, which helps dispatch it to the hardware and helps you do loop vectorization. So from there, your for loop call can then actually be vectorized across the processor and then done in SIMD parallel, right? So with that, instead of just operating on each one of those, for every one of those iterations, you're operating on the loop. And this is really where NumPy and other performance libraries come in handy, is you don't have to basically be locked in Python. And a lot of numerical work, be it linear algebra, does a lot of loops, right? So in so doing, this is very, very useful when you're operating on any type of math, science, engineering kernel. So let's talk a little bit about the native performance libraries. right? So you have the tools such as the math kernel library, the MKL, which allows for mathematic linear algebra to operate a lot faster with natively written, and it allows you to use that library to actually program for Python packages. So if you want to make your own package that does something very specific, you can use the MKL to do so. You can write those programs and build them with a light kind of Python wrapper. And it also allows you to bypass the Python layer immediately. And so, as I was saying before, that bottleneck of the global interpreter, by using one of the performance libraries or using a performance framework, like I showed before with NumPy, you can get out of that kind of that Python layer. So, going back to what I was saying before, when you look at the term Python performance, it usually means getting out of that main Python layer and doing something specific in the domain space you want. And that's where the performance libraries and some of the other kind of tricks that I'm demonstrating here allow you to get. So for the type of work that you do, if you're going to start to do anything in that numerical, scientific, engineering space, these are the type of things that you want to be utilizing to get accelerated Python. So again, it helps target vectorization, and you can convert scalar implementations of many commands into vectors for SIMD hardware. And again, the loop vectorization is going to be the most important, because where you can reduce the basic single-threaded loops is where you're going to see usually the biggest gains. And you can operate with one single SIMD command to have a lot of data operated on in parallel. It also helps you utilize your full hardware. So say you actually program something for your laptop. Say it's an i5 or an i7 like I have here, and you then move it to one of the higher end servers. You can take that same code and it'll dispatch correctly from what was on here and the instructions that were on here, and then say the other one has AVX 512 or something on there, then it'll actually dispatch to that one correctly. So that's where I can actually write my code once, and I've been really happy to show some of those examples before, which is like I programmed something for a laptop, it operated in pretty decent time. I throw it on a really, really big server just to see what it'll do, and it does it in like 1/100th of the time. I didn't have to change anything because it's using Python and a native performance library, and when it goes to runtime, it'll actually dispatch correctly based upon the hardware. So in terms of not having to reinvent the wheel, it's really useful when you want that code portability to be present. But in the instance that you do want to use something that's a little lower level, let's go over an example of where that would be used. So an example of like the math kernel library, I'm going to show you a very simple kind of screenshot of one of the examples that we have, which is the sine and cosine example. So say your numerical calculation or any type of computation requires the use of sine and cosine. Well, instead of using that at the NumPy layer, you can use kind of the native performance variant of it at the C level, which you can program directly. It does require a little bit more work, so you are trading off some of that flexibility for higher performance. But when you actually want to get the most out of your code, or you know that it's a very domain-specific application that is bottlenecked by some part of the secondary framework, then you can get around it by actually implementing it directly. So this is just an example of one of the APIs that you can use to perform that. But in a general sense, as you get farther and farther into whatever calculation you're doing, the usual process is you'll start with the Python example, and then you'll hit a bottleneck. You'll see if you can get around the bottleneck. You may go distributed, you may go another format, and then you'll eventually dial down where you may have to implement this directly. And so for a lot of actual, one of our biggest areas that we see this is astrophysics, and I would say material science. We see a lot of them having to go directly down to this layer to get that performance, but you can usually prototype it and run a good percentage of it while still at the Python layer without as much dependencies as this will entail, right? So let's take, for example, a loop in general Python. So this is done 100% in Python, right? And it's just an arbitrary, we're just showing an example if you had to do a loop example with a square and sum function of some sort. How well do most of you think this will operate? is this what some of your code already looks like? You just make a loop and you do stuff to it. You think it'll perform well? It'll just be Python, right? It'll be single-threaded, looped. It'll perform okay for you having to make an iterated variant of it. So if I do this, how well do you think this will perform? So I've essentially taken np.arrange and created the 1 to 1,000 numbered array, right? Up here, right? I've also used np square. So how well do you think this operates? Do you think this will be better? It'll actually be worse. Can anybody tell me why?
Is it having to transfer the data back and forth between the C interface? Is that the?
Yes. So it's having to basically individually pick out what you did in the NumPy array and iterate it in a Python for loop. So this is actually not using vectorization. You're actually doing it worse by having two constructs and jumping back and forth, right? So the problem that actually is the improper use of NumPy array. So you caught that one. And we're individually selecting those, but not using it as a vector, right? And that's kind of the big problem that we're doing. We're not using the native framework. We're not thinking in the format of what essentially is that performance library or the concept of what data parallel actually looks like, right? So loop vectorization, again, is what we're trying to use with these NumPy arrays. So how do you think this code should change for this to work? Anyone have any suggestions? Go ahead.
We should pass the entire array to NumPy
Mm-hmm.
and then do all the calculations in vectorization.
Correct. So the correct one would be, as he said before, is to actually pass the entire thing to NumPy as the entire vector and have each of the constructs call within NumPy the correct levels. This is actually operating on that entire array at once. And that is the power of NumPy. Essentially, it is doing that process for you. It is operating on the vector. And through even, I guess the n-dimensional type of arrays, if you know what you're doing, you can actually optimize for this type of work. It does take a little bit of learning if you've never seen how NumPy works to understand how this actually operates. But being conscientious that actually is a thing and looking at your code and profiling your code is very important. So if you profiled your code, you'd see that it's actually worse. And we can show you an example in a sec. I think I should be able to actually do that right now. So let me see. Right. So in this instance, right, so we have this one, and if we run time it, right, it takes 330 microseconds, right? And then if we run this one, which is that kind of improper one, it's much worse, right? So these are all kind of things that you can do actually in Jupyter Notebooks, which I think will be used pretty heavily in the next section. So for those of you who are playing with this, the Jupyter Notebooks are really powerful. I use it pretty much every day for my numerical work. And you can do kind of these little magic functions inside of them that allow you to do basic profiling. I'll usually go to VTune for the bigger stuff because it gives me a lot more insight to what's going on. But this is just kind of a litmus test to go, there's something wrong with my function, right? But this one actually, aside from one that got intermediately cached, 6.72 microseconds, right? So there's a pretty big difference, and this is one of the reasons that you should really kind of look and see what your code's actually doing and understand what's going on behind the scenes, or else you're going to be bit by these problems, which you think you're doing the right thing, but you may not actually be doing it. And this is also, if you have different computers, I would actually say go use the NumPy variant and see how it operates on each of your different pieces of hardware, because as you go up kind of the chain of processes, you'll see that when it dispatches to hardware that it gets faster and faster and faster. Okay. So in other forms of numerical calculations, right, you have a lot of other specialized ones that NumPy and SciPy can do, such as FFT and signal processing. And for one of the more popular ones, which is like kind of matrix multiply, the loop that we showed was NumPy in a kind of a basic single loop. But when you start going into kind of a matrix, how does that change, right? And the matrix math is used in a lot of different fields. I mean, it's used pretty heavily in machine learning. It's used a lot in just general engineering. So when we actually implement this, what is NumPy doing for you? Where is the performance coming from? And how do you utilize it and detect it, right? And so, so just kind of a show of hands, how many people are more in like the mechanical side of things? Okay, electrical. Okay, so we have a pretty good split, right? So if you solve circuit systems, I'll occasionally use these to do some solving of some of the circuit systems. Back in the day when we didn't have Python, it was through other more primitive means. So consider yourselves lucky for some of these. But yes, the matrix math is used pretty heavily in a lot of fields. So this is one thing that would be good to focus on and learn probably the NumPy variants or learn the actual C variants if you're going to be implementing stuff on larger code. So let's look at a pure Python example of this, right? And it's manageable. It's just several for loops that iterate and help you do that calculation. It's not the cleanest. This is what we normally see, and if you see people in a Python class in CS, this is the very first thing that they'll try to do is show them what the matrix math will be. But when you actually do this, obviously that example is in pure Python, so you do have one less dependency, right? You're not calling anything else. You're still limited by the global interpreter lock, which means that it's literally going through every one of those steps every time. It's not parallelizing anything. You're trading that loose typing, obviously, for performance and a larger memory overhead. So how do you actually get the higher performance from what we just saw here, right? And the key to doing that is to actually use the optimized libraries for that. So you see how verbose this is, right? In NumPy, it's pretty small. It's incredibly small. It's just dot, right? So np.matrix, I just use it to just force it into the correct data type. I mean, if you already built it inside of the NumPy array, you wouldn't have this problem, but I'm just showing you an example of it. And then you use np.dot or just NumPy if you haven't imported the namespace. And that will give you the matrix multiplication with full hardware vectorization, right? And that is, one, you're getting the best out of your hardware. Two, it's a super concise syntax. And it's a single line that can call and utilize the full vectorization from hardware. So in terms of utilizing the numerical, the native performance libraries, using NumPy is one way of doing that because it's actually calling to it with our distribution. And if you want to get more of it, you can continue just using the native performance libraries, which some of us have done before. And hopefully some of you may eventually do for some of your really high performance code. And for most, that's enough performance for most people to get out of it. I think 80% of the people that we know will usually stick in NumPy, but then we're seeing a growing number of people having to step out of that range to actually implement this code in production in a even higher performance setting. So then they'll have to go directly to the tools such as the Intel MKL to operate on that. So again, when I talk about the BLOS interface occasionally being the bottleneck, what I mean by that is if you have NumPy constructs that you're essentially having to go back and forth and they're not exactly fitting what NumPy was designed for, you could be incurring some penalty within the API itself, right? And so actually dropping that layer and going directly down into the C performance side of things will help you negate that. But in so doing, you will have a little bit more maintenance work to do. But you get amazing performance. With the Intel MKL, I'll show you the example of what it'll look like, and this will just be a very short, quick example. We are operating at the sea level, so there's a little more work that has to be done. You can either build a wrapper or a package around it. I wouldn't say it's super, super heavy to do. I don't know. How many of you are comfortable programming in C? Okay, so an okay amount. Okay, that's good. You'll probably have to do it at some point. This is the verbosity that you'll eventually encounter, which is that if you want to do something like dgem or gem, which is a specific type of calculation that requires a lot more setup, then you'll trade off a little of that flexibility for the high performance that comes with this. But the point is from this calculation, say you actually have to stay at this level and operate on this directly, on something that NumPy doesn't support or SciPy doesn't support, then you can implement it directly and have it never leave that layer of C. So the performance will be highly optimal. And obviously, the best way to detect this is through profiling. So using tools like vTune would be a great option in that case, because then you'd actually see where your code is actually getting stuck at. And if it's getting stuck at that layer, then you probably will have to drop down to the lower level library to achieve that vectorization and high performance. And then when using that code, this is kind of an example, just kind of a trivial example of how you would use this code. And this will definitely outpace NumPy on many occasions. So using the MKL directly is really, really useful when you implement really anything in the STEM field, in my opinion. Back in the day, I really didn't have that much experience with it, but now that I'm actually in the space and seeing a lot of what the customers are doing, these are the type of flows that we're going to see a lot more of in industry. So understanding what these are and how to use them is really useful. Okay. So again, think about the trade-offs that you're willing to go for and to achieve that performance. So for kind of a general example, I don't really want you guys to focus too much on this because this is more from the financial world, but just look at it in terms of numerical work. It'll look very similar probably to some of the numerical work that you've seen. This is the Black-Scholes algorithm, which I'll show in a minute, and this is an example of actually using the Intel Performance Library, starting from a pure Python example all the way to a highly optimized example, what you can do with that code. Okay, and this is a great example of problems that exist in the real world. This came from a customer, and so we worked through with a customer to kind of understand and help them implement a solution that would work for them, and kind of step through the different layers of optimization. So again, don't worry too much about understanding this algorithm, but just see that it does have second order. It does have it is a PDE in general form, right? And then we're essentially trying to solve it for the call and put options, which are I think there's two parts of it, which are D1 and D2, and then the C and the P are the call and the put. I think you can find this example online pretty easily. So now let's try to put this entire messy thing into Python, right? So the Black-Scholes algorithm will look like this in its general form in Python. It generates the intermediates that I was showing you just a second ago. So you'll probably have to generate two intermediates, which are the D1 and the D2, which are W1 and W2 in this example, and then go drop into the D1 and D2. It then calculates the final call and put options for each of those, and then returns that to the user. In this case, it actually puts it into an array and hands back everything to the user. So when you run this, this will look very interesting under the watchful eye of profiling, right? So if we're going to be, I'm showing this example specific in vTune, and that's because we'll go into higher performance library, so I'll need that for that capability. But we're going to do basic hotspots on the code that I just showed you. So we're actually going to put that into a Python script. We're going to run it with a Python binary as the option. I'm going to move this forward a little bit. And when you actually run that calculation, you're going to end up with a profile, just kind of giving you an understanding of how much time did it take, How much of the hardware vectorization did it use? What other details can we see on it? And one of the nice things about VTune is you can actually see Python and other mixed code put together and see how well it did by itself. So in this case, we actually see a kind of a graph of what things took the longest and what it looks like on the system. And then from there, we actually go to kind of our code base's largest time taker. And so if we actually go in there, it'll load up the source code and show you what things actually took the most time. Okay? So one of the things to also notice is that when we go to the next example, this example took about 0.7 seconds. And it's actually, I think, it's the invert square that took the most time. It's because, one, we're not using the most optimized invert square. We're using the basic math library from Python. We're not using an optimized invert square. We're not using optimized error functions and square roots and other things. So when we start getting into those areas, you'll start diving in. And this is actually just showing call stacks. So you can kind of climb up and down the call stack to go look for where a problem might actually exist. But yeah, we'll move forward here. So now, in light of what we did in the other example, where we actually achieved loop vectorization by removing the for loop and using the full power of NumPy in this case, right? Notice that there is no for loop now, right? We're operating it as one continuous vector, right? So we're passing the entire vector and we're doing the calculation as is. And by using the proper array types from NumPy, we'll be able to utilize all the hardware in this case and step around Python as much as we can. How much performance gain do you think there will be generally in this example? 5, 10, 20%? Okay amount? All right. So this was from the previous example, and then now we're actually going to go look at the NumPy variant. So the NumPy variant actually took about 0.5 seconds instead of 0.7 seconds. And just looking at kind of the information that's provided, you'll notice a couple things off the bat. You actually receive more information than you did from the previous example because it's using the rest of your hardware to do it, right? It's profiling and saying, oh, you're using multiple cores, you're using, you're using OpenMP, you're using a lot more aspects of your hardware. Even the system profile looks different. You see at the end, there's a lot more differences at the end. Now, one thing I will say is that you will have a harder time looking inside of performance libraries. So if you're going to profile something like NumPy, it's really hard. Mostly because if you're looking at that level, then you probably should be actually using a performance library if you find NumPy to be the problem, right? Because unless you're willing to push a lot of changes to open source or explain why that your code, your example has to be optimized versus everybody else's, then that will be a very hard sell. Another thing also, you'll see how different that the profile looks in terms of its breakdown in time. And that's because of the fact that it is calling down to NumPy. Now, one of the things you will lose if you don't build it with the debug option is you won't see into NumPy, like I said. If you build it with debug options, you will see into it, but then you'll hit your other second harder point, which is you probably shouldn't be, you should probably be exiting, either optimizing your code in NumPy or exiting NumPy itself. Okay. But one of the things, again, to notice here is that when using a high-performance library, you will see a dramatic change in profiling as one way to ensure that you're doing it in the right direction, right? You could be going the wrong direction on occasion, like I showed with the incorrect NumPy usage. So make sure that you profile and understand what you're doing. Usually, I profile any type of numerical code after I'm essentially done ensuring that the answer is correct. And that its operation is correct. So that's that point of optimization that I'll continue looking. Right. So what exactly changed in that is that we leveraged the native performance libraries at the NumPy level. And so the purpose-built frameworks really boost your performance in that sector. It helps you get around the problems that you saw in the previous example. And you can greatly improve your productivity just by using Python as glue code after the answer has been returned. That's typically how I look at it. I send the function down to I send my calculation down to something that's more specific, and then I pass the answer back, and then I go to something else. And so it's still operating in that kind of glue layer, which is where I think Python really shines with all of its tools that it provides out of the box. Now, in that light, you also want to learn what operations can and can't be done in NumPy and SciPy. They're very powerful libraries, and typically most of the stuff you see in school can actually be done in those libraries. So learning both the API and how to properly use them, like I was showing you just a second ago, is really, really useful, because at some point you're also going to probably hit some type of senior project or something in industry where you're like, I need to figure out this calculation. Like I had to design a filter, an analog filter, and I was trying to do it in something else, and then I just did it in NumPy and SciPy because I knew the commands, and I got my answer a lot quicker than most of the other students. It's just a good example. If you have to do that type of stuff in industry where you need to get, you're on a deadline, then using this as a tool to leverage that is really useful, because it's optimized, it's very expressive with less verbosity. So that's where the real thing about Python can come out and shine. So with the native performance libraries, there's actually a lot of them that can be used. So we have the math kernel library, which I was just demonstrating, which is more numerical and scientific kernels. You have the integrated performance primitives that really focus on things such as image processing and text processing. You have the data analytics acceleration library, which focuses on things that are critical to, say, machine learning or data analytics type of operations. And these are all kind of low-level libraries. Then you kind of have a different one, which is the C compiler itself, or ICC, thread building blocks, and the MPI library. So some of these I'm sure you have already heard throughout this series, and you really want to build upon those packages if you want to leverage the most out of your your math, scientific, and engineering kernels. So in order to use them, you usually will have to, at least at the Python level, you're going to have to write some type of wrapper layer in order to use them with your other Python code. The purpose-built libraries can be matched up and utilized with your other Python code, and staying within that frame, that layer allows you to use things such as NumPy and SciPy as long as you can achieve it in that layer. So making, you kind of have to look at your needs and understand whether a lot of your workflow is going to be in Python, and then continue that work once you know where it's going to be. You're going to look at the performance packages that are going to be required to get the task done at hand. And then the advantage of using kind of the native performance libraries is you can scale as your needs grow. So if you have a certain calculation that you're running on your laptop, and like that example that I gave, and now you want to run it on a larger compute server, you can do so with essentially no code changes. And that's one of the advantages of Python, is that you don't, if you're using, like, say, the Intel distribution for Python, which actually is built with most of the libraries I just showed, then when you dispatch it to like a larger server, you don't have to make any code changes to your Python. You can just maintain it and stay in the Python layer, run it up there, and you'll get all that performance for not free, but you will get it for the price that you paid to implement it in Python. So with the performance that you can get for just general Python performance, there's kind of three classes that I would look at when talking about this topic for numerical workloads. There are the compiler optimizations when you build the base Python binary. So remember when I was talking about kind of the 4 steps that the Python interpreter has to go through to get from Python code to operating on your work, right? You can do stuff at that level, which if say your entire work is in the Python layer, then you're going to be using the compiler optimized Python to actually get through that. Next, you would actually go to the optimized libraries, and that's kind of the next step, which I was showing. So then you'll be using NumPy, SciPy, scikit-learn, whatever you want that operates at that layer that's purpose-built that can operate with those native performance libraries. Next, you actually have the just strict Python vectorization frameworks. There's a few other ones that actually achieve vectorization without using, say, the complete C library and allow you to stay in Python. We'll just kind of go over those in a sec. But there are other tools to achieve vectorization if they don't fit NumPy exactly, but you still don't want to go into the C layer. So when looking at the compiler optimizations, when you're building your base Python library, you can use ICC instead of GCC to build the Python binary. And so that will gain you some level of performance on, on Intel hardware. And then it also allows for better vectorization and hardware utilization at the compiler level for the base Python language. And it's just kind of an easy way to get low-hanging fruit from the Python code. If everything is essentially in the Python layer, then that's kind of your best bet. Next, if your workload fits more of the math, science, engineering calculations, then you can use the tools that can utilize the math kernel library for your purposes. So NumPy, SciPy, et cetera, is kind of your best bet. Or if you need to use the direct native performance library, such as the Intel math kernel library, to write your own functions, wrap that in Python, and then use it at the level that you care about. The use of Python code bases in that is such that you can get your workflow and keep others' workflows within the Python layer, and to utilize the MKL with NumPy and SciPy. Now that, this is kind of the layer where you either have a good understanding of what domain problem you have, or you're okay with the trade-offs that come from writing it in C and then writing a layer around it and then handing that off. There's kind of a third in between one that you can actually choose with it, which is the specialized vectorization libraries. And so two of those examples are, and very distinct examples in Python, are NumExpression and Numba. So have any of you heard of either of these libraries? Okay. So NumExpression is numerical expression, and what it does is it takes your symbolized mathematic computations and puts it directly into vectorized code. Its syntax looks really weird. I would suggest you go up and look at it. It's pretty neat, because when you know what your algorithm looks like, you can actually implement it all in one command, and it'll parse it all for a vectorized command, but it really only fits in the numerical and scientific space. For other things, this may not be as useful. Numba jits the code, or just-in-time compiles the code. And then it makes you, essentially with that, you're paying for the upfront time of compiling it at that time and then using it afterwards. So the upfront cost you have to be willing to deal with. But it also is another way to achieve that vectorization, because during that compilation stage, it'll actually go and do something similar. And so the libraries actually directly work with those two frameworks work directly with the native performance libraries to achieve vectorization and performance. From Python or symbol code, and then you can use that at the Python layer, or you're essentially getting an even lower MKL level to run than, say, NumPy or SciPy, because you are directly interacting with the vectorization layer. And allows you, again, your code base to stay completely in Python. So for some of our customers, making sure that they don't exit that layer and they allow their data scientists to stay at that layer is really useful, especially when you have like a deadline to meet. Some of them, instead of like trying to mess with the compiler, will just actually go directly to this if they know what their problem is. Now, there are things that are not supported by this. It doesn't do certain types of calculations that are not supported in the vectorization conversion. So in that instance, you'll be better off working directly with the MKL, because you'll get the specialized functions that are in that numerical scientific space versus just symbol code from algorithms to actually be converted. Now, if none of those help you achieve your performance, you can step out of just the local node idea completely and just go distributed for other types of parallelism, right? So you can use MPI for Pi, you can use Dask. There's actually another example, which is with partial static compilations with Cython. So Cython is kind of a package that compiles down to C from your Python code, but it's Cython code. It looks like Python code, but then it kind of enforces that some of your things are static. And so you'll trade a little bit of your code flexibility in to get that performance. And it gets an okay amount, but usually it still won't beat out straight C, even though it is written in C. But it does give you additional flexibility if your code doesn't fit that. But it does require an upfront compilation in order to use. And then parallel and distributed computations, mostly distributed, will help you achieve that. So you'll see a lot of Python frameworks actually that are popping up for distributed workloads, and that's because they understand their needs and they're able to know what parts they want distributed and how they want them distributed, and they can stay within the Python layer. And so they're starting to cater more and more because people from industry are coming from, say, other fields aside from engineering, and they're introducing the distributed system parts of industry that are required for those industries into the Python ecosystem. So that's why you're going to start to see a lot more of them coming up. And one of the things that I generally will tell our customers if I'm working with them is that you want to look at your code base as a whole, and where you want your performance level, you may have to move that slider of how much is C code and how much is Python code, and kind of tweak the knob based upon what things you're willing to do now and what things you're willing to do later, and kind of just grow your needs based upon change your code base based upon your needs at the time. So the types of computations that are done in engineering, this is kind of a small list of what you guys probably will be relatively familiar with. These are the types of calculations that luckily are supported by NumPy, SciPy, etc. And so when you go to, say, an applied field of these type of computations, you will then go have specific needs where you can actually, again, take out the native performance libraries to step around some of the Python layer that you may need to escape. So some examples of these applied computations are going to be kind of the filtering DSP signal conditioning that I think for some of those that are in electrical engineering, you'll be using this in embedded systems or any type of telemetry kind of IoT areas. You'll see a lot of high usage in this. Advanced statistical calculations, so you'll see a lot of kind of statistical methods and kind of leading into machine learning use kind of a combination of what I just showed before. And then mechanical materials and physics simulations use a lot of what I showed before. And so as you basically compose those bits, you'll see where, if you understand where, say, the MKL functions are, you can start assembling them based upon what pieces are from where. And so an example of that would be, like, say you have the infamous kind of linear least squares fitting, right? So you have something that you need to minimize based on for best fit. And you can then take some of the specific MKL functions and compose them together to achieve that operation. And so can anybody tell me what this possibly could be used in, this function?
It's used in error analysis and predictions.
Right, predictions, right? So this is actually, there's a form of linear regression that uses this, right, which hopefully you will see in the next series, right? And so, again, when you get to kind of applied fields, you'll start seeing kind of the base pieces of what the numerical and scientific fields, i.e. things you'll see in NumPy and SciPy, assembled together in different ways. And that's where, using the either NumPy or SciPy, or in this case, the DirectIntel MKL is really useful because you understand what things were created for what purpose, and then you're actually creating something that's optimal and achieving the best performance that it can on a given piece of hardware. So we're going to actually just take a short example look at this, and we're not going to do too much with it, but essentially there's a few functions in the MKL that we're going to be using. We're going to be using, I think it's get sy, gel sy, and etc., like the ones that I'm showing here. And then you can take those and then you actually have to put in a little more information that you would standard to NumPy and SciPy in order to get it done, but the trade-off is worth it. So then when we build it out of the we'll then build it out of the Python example, right? So this is just kind of an example of the inputs. I know it's a lot of screen space to be looking at, but just understand that, you know, when you actually start assembling it at the lower level libraries, what it will look like. So the inputs will be that. The output will look something similar. Sometimes it'll do it in place and hand you back a pointer, which I think this one might. I think it hands back a pointer. So when you get that, you'll be able to get you'll be able to call that function and get the answer and then do something else with it. So if you need to stay in that layer, say you have something that's really not supported by NumPy, SciPy, or scikit-learn, you can actually operate on that at the C layer and then pass it back up to that. In the example where you do just care about using it only at the top layer, right, it's pretty easy. You can call it directly from SciPy. That's kind of how it's built underneath the hood for some of those. They may have a little more type checking and flexibility, and that's if you're willing to throw some of that away for even higher performance, then using the native performance libraries is a great example of how to achieve that. And for customers who have really dedicated flows in production, you'll be doing a lot of that, right? You'll be saying, well, we kind of know what's going to go in here. We can throw away these 4 checks because we know exactly what type of data type is going to come in, right? And type checking actually takes up a significant amount of time, so that's one of the things that you're more than willing to throw away in those cases where you know what stuff's coming in and what stuff you want coming out. And you know, with this example, you'll see that, you know, for say scikit-learn, which uses this, is actually composed on top of this function. And so if you for higher performance, you know, there's a few native performance libraries that we use to actually get around this problem. So we actually use the data analytics acceleration library from before to actually implement this directly inside the linear regression method. So we actually don't even use the MKL. We actually use something even low, kind of that's more dedicated in the C world to actually program up for that layer and then give it to you at the SciPy. So for those who are using the Intel distribution for Python, right, we're actually implementing. So instead of actually using this as a component inside of linear regression, if you're going to recall the linear least squares variant, we're using something that's a lot lower level to achieve that, actually all the way down to the data analytics acceleration library to get around it. So we do deviate a little bit from the changes that we have when we make some of our high performance Python products, such as the Intel distribution for Python. And so that's where we're essentially getting the performance for you, and that's why you essentially get really, really good performing code when you use our variant of the distribution, because we make those code changes for you instead of just sitting on the standard NumPy, SciPy stack. So in summary, the reason that, you know, obviously math, science, and engineering has picked up Python, I think after you see what this presentation has shown you, you can see why it's gone that direction from the emergence of the numerical frameworks that have kind of emerged in the space and really been used by the industry. It's kind of a no-brainer to use Python in these cases. It's also becoming the language of choice for many of the engineers and scientists around the globe. So, you know, I just came back from EuroPython, and you know, the way we speak about Python, we can, even though we may not actually have a language in between that we can speak, we can just show Python code, we all understand it. It's kind of neat. So there's, you know, around the globe, you're starting to see a lot of people use it, and that also means that, you know, the type of work that's being done in the open source space is also increasing, and that's why, you know, for many of you, why this, you know, it's kind of important that we teach Python in this case. And one of the other things that it does really, really elegantly is allows you to access those performance libraries relatively easily. I showed you, 4 methods of how to achieve that already, right? You can, you know, you're able to use the MKL directly. You can put a Python wrapper around it, right? You can use NumPy, SciPy. You can use some of the other escapes of Python vectorization without actually using the direct C API. So with the uptick in usage, I think it's really important that you go in and you explore and you understand what each of those packages and frameworks can offer you, and then from the native performance libraries, what they can offer, and take that into industry with you. Right, and the types of performance gains that you can get in the Python realm, right? You have kind of three big pillars. You're gonna have one of the libraries, right? The libraries, frameworks, etc. You're gonna have one of the compilers, and then you're gonna have one for additional parallelism tools. So you have three really, really big pillars that you can stand on to achieve high performance Python code for numerical, scientific, and engineering work. And for kind of the advanced usages, right, because a lot of the applied kind of fields that we have today stand on top of linear algebra components such as machine learning, right, and matrix math, those type of accelerations are carried over easily because kind of the fundamentals are still in the numerical kind of computation world. And then many engineers and scientists will also be using interpreted languages in the future. We're seeing a huge uptick in just general scientists staying in kind of interpreted languages because of the speed at which their work changes. Their workflows change so quickly now, and the size of data sets that they're able to operate on. Sometimes they want very flexible languages to work on them. And we're seeing just a huge uptick in that. And I think for colleges and stuff, it's really important, not only in the academic space, but now as those scientists become, either stay in the science field or continue into industry, I'm seeing that even say the data scientists within industry are continuing to use that. So for those of you who are going to enter or are going to graduate pretty soon, I think it's a great language to pick up and learn and get your general stuff done. It's also really useful to process text and other things. I use it to do other fun stuff. I do it for my website and everything else. So, it's a very flexible language for you to learn and explore and do other fun things with. And hopefully, with this presentation, you'll understand how to achieve high performance Python. All right. Q&A?